Hi, good morning everybody. Let's take a look at question 1 of the FA. So for question 1 is merely just drawing dot cross diagram in order to determine what is the bond angles and hence predict the shape of each species. So for CHCl3, we know C has 4 electrons, H has 1 electron, Cl has 7, 7, 7. So in all these cases, 1 and 7, so single bond. So carbon should take the central atom and H, Cl, Cl, Cl. And then carbon should have the electron, maybe let's assign it as a dot. Okay, and single bond each. You do not actually need to differentiate between the electron of hydrogen and chlorine, okay, because in this case we are talking about dot and cross diagram, just dots and crosses will do. So for chlorine, we still have 6 electrons left on each chlorine, so just fill it in. If your diagram is incomplete, it will be taken as wrong for the entire diagram. So this will be your dot and cross. So for bond angle, we need to think about how many bond pairs and lone pairs. So around the carbon atom, we actually have 4 bond pairs and 0 lone pair. So that's why it will be tetrahedral and 109.5. This one you really have to remember the table in the lecture notes really well. For SO3 2-, let's do an assignment again. S will be 6 electrons, oxygen will be 6, 6, 6. But over here I have 2-. 2- means add electron to more electronegative atom, which is my oxygen, and they will take 1 oxygen each, so plus 1 plus 1, so altogether 6, 7, 7. Okay, that means 6 means a double bond, 7 means a single bond. So based on this, I let my sulfur be the central atom, 3 oxygens surrounding it. Okay, so for a double bond, I will do something like this. So on the oxygen, still left with 4 electrons. And for the 2 single bonds, okay, so this is a single bond. Oxygen still left with 6 electrons because it has 7 over here. So the other oxygen and sulfur will have a single bond, and on each on one oxygen there is 6 electrons left. Okay, and we are referring to this oxygen. So let's take a look at sulfur. It has 4 electrons being used up, so I'm left with 2 more. So I can just squeeze it somewhere here. Okay, so not to forget, I need an overall bracket with a 2-. Without this bracket, okay, and the 2-, you will get your answer to be 0. Okay, so to determine the bond angle, I need the lone pairs and bond pairs. So in this case, I will have 1 bond pair, 2 bond pair, 3 bond pair, and 1 lone pair. So I have 3 bond pair, 1 lone pair. So if you remember, the shape will be trigonal pyramidal and it will be 107 degrees. Okay, and then just to take note over here for sulfur, if you count the number of electrons around it, I have 2, 4, 6, 8, 10. I actually have 10 electrons, which is more than 8, but it is okay because sulfur being in period 3 can expand its octet. Alright, moving on from here, ICl3. So for ICl3, let's take a look. I will have 7, chlorine also 7, 7, 7. So it means in this case single bonds. Okay, so I will be the central atom because I is less electronegative, okay, to be the central atom. Put the chlorine around it. Okay, so in this case, single bond, so okay, the other side also single bond. Okay, then on iodine, I used up 3 electrons, so I'm left with 4. So place it in 2 lone pairs, 1 lone pair, okay, and 2 lone pair. So based on this, let's take a look at the shape. Of course, we have to consider bond pairs and lone pairs again. I have altogether 3 bond pairs, okay, and 2 lone pair. So 3 bond pair, 2 lone pair, the shape will be T-shaped, or okay, T-shaped, and that will be the answer. Okay, in this case, it's already given in a question. So just as a recap, finally for dot and cross, you notice that I do not need to show the shape of the molecule. So over here, some people are misled by how they draw the diagram. It looks like a trigonal planar, but of course, because this is a dot and cross, we need not show the shape. But if you draw in a Lewis diagram, then it will actually be a T shape. Okay, this is actually just a recap for all of you. If you draw the Lewis diagram, it will actually be a T shape. Okay, and of course for iodine, I need to show my lone pair in terms of dots as well, because this is my Lewis diagram. Okay, for Lewis diagram, just a recap, I must show the shape. I also must show all lone pairs in dots. Okay, so this is my T shape. So take note. Okay, for question 2, right, it is quite similar to question 7 or 8 of your tutorial, okay, whereby they ask you to explain the following observations in terms of their structure and bonding. So for 2A, they mention at RTP, carbon dioxide is a gas, whereas silicon dioxide is a solid. So once you see a gas, you will think of boiling point. You see a solid, you think of melting point. So in this case, this question is just about how structure and bonding link to the property, which is our melting point or boiling point. So straight away, we know that we need to structure our answer in terms of SBE, okay, structure, bonding, and energy. Let's take a look at the answer. So in this case, you notice the answer is very systematic. I have carbon dioxide has a simple molecular structure, so this will be my S. Then, of course, moving on to bonding, there are weak van der Waals forces between the molecules, okay? Once again, I would like to highlight the importance of writing between the molecules, because you need to mention where the van der Waals forces are. If you don't write this part, even if you write van der Waals forces, you will not be given the half mark. And finally, E, okay, for energy. So weak van der Waals forces require only a small amount of energy needed to overcome. Okay, so for CO2, we have our SBE. For silicon dioxide, it is also very systematic. Giant covalent, okay, structure, so this is our S. Then for B, it is simply just strong extensive covalent bonds between the Si and O atoms. Okay, please take note of this part. You need to have, again, between what? A lot of you forgot to write between what, and even though you wrote strong covalent bonds, you don't get the credit. So please be very precise in your answers. Then finally, E, you have large amount of energy needed to overcome the strong covalent forces. Okay, that's why in this case, CO2 is a gas, whereas SiO2 is a solid at room temperature. So SBE for each compound, which is very systematic. Okay, for next one, 2B, we are talking about aluminum chloride and arsenic hydride react in a 1:1 mole ratio to form an addition product. Draw the structure of the product showing the shape. This question is also from the tutorial. Okay, let's take a look at the answers. So they want you to explain the observations. So in this case, we need to explain why they actually react in this mole ratio and why it gets this addition product. So of course, we need to talk about AlCl3 first. Okay, so just as a recap, okay, for our addition product, okay, don't copy the answers first. The thinking process is very important. For addition product, okay, of course we need to have a donor and we need an acceptor. Okay, so our donor, of course, donates a lone pair of electrons. Okay, donor, donate. So acceptor, you need to accept lone pair of electrons. So that means the acceptor must be electron deficient. Okay, electron deficient, and hence it must be short of an octet configuration. Okay, this is just a quick recap of what our addition product consists of. Okay, it consists of our donor and acceptor. So in our answer, we need to talk about both of them systematically. Okay, let's take a look at our acceptor first. So our acceptor in this case definitely is Al in AlCl3. Okay, you need to mention this whole portion. The Al in AlCl3 is electron deficient. Okay, that will give you a half mark. And you need to mention how many electrons does it have short of an octet configuration. So in this case, it actually needs 2 more electrons to gain octet configuration. How do we know that? Well, AlCl3. Okay, so this is our AlCl3. Okay, this is the Lewis diagram. And you notice that around the aluminium atom, I only have 2, 4, 6 electrons. Okay, over here I only have 6 electrons. So that means I have 2 more electrons in order to gain octet electronic configuration. And that gives you your half mark. Okay, so if you take a look at this, we have already talked about the acceptor. Let's move on to the donor. Okay, so for the donor, of course it must be arsenic hydride, because let's try to draw the Lewis diagram again. Arsenic is actually from group 5. So after forming 3 single bonds, I should have 2 lone pairs left over. Because if you see ASH3, this is 5, this is 1, 1, 1. Alright, just a quick recap. So if you notice, I have a lone pair here. That means ASH3 must be the donor. So we must describe the donor. Okay, ASH3 has a lone pair of electrons available for dative bonding to AlCl3. And hence, finally, it can form a dative bond from ASH3 to AlCl3. In this case, some people actually wrote dative bond between ASH3 and AlCl3. And AlCl3. In this case, this is taken to be wrong, because for dative bond, you need to indicate the direction, because dative bond has an arrow. So by saying between, you actually don't know whether is it A to B or is it B to A. Okay, so in this case, you must specify from what to what. This is important. So finally, draw your diagram. You should be showing a dative bond from arsenic to aluminium, okay, including the lone pairs, and this should be your correct answer. Okay, and of course in this case you also need to pay attention to the shape of the molecule. Why do I say that? Because some of you actually draw your answer in this way. You draw your arsenic, you draw your aluminium, and you fill in all your hydrogen followed by Cl, Cl, Cl. Do you notice what is the difference between these two diagrams? Well, I hope you do, because for the wrong diagram, I actually have all my bonds angles in 90 degrees. So this is wrong, because the shape of the molecule is actually tetrahedral. Okay, I would like you to take this down. The shape is actually tetrahedral with respect to both aluminium and arsenic atom. Okay, some of you put octahedral, which is wrong. Okay, so please take note. And if you like, you can put the bond angle on the diagram. So this is actually 109.5. This is also 109.5. This is also 109.5, 109.5, 109.5, 109.5. So on the diagram, of course, it looks like some bonds are bigger than the others, but in the 3D format, okay, it is actually the same bond angle of 109.5. Okay. So let's move on to question 3. Okay, for question 3, I won't go through systematically with you because I think most of you got this correct. The main thing is really just to remember your formula properly so that you won't actually get careless mistakes for this. So it is our deflection angle is proportional to charge over mass. Okay, in this case, another careless mistake could be you left your answer in 3SF instead because the question mentioned they want it in 1 dp. So please take note. For question 4, actually it is also a very simple question. Okay, it's actually just in our lecture notes and tutorials, exactly the same. It's really exactly the same. So let's take a look. The question mentioned ammonia gas shows marked deviation. That means deviates a lot from the ideal behavior. So under what conditions of temperature and pressure is the behavior of ammonia most nearly ideal? By saying this, that means they want ideal. In what condition, under what condition will it be ideal? Okay, so this part, all of you shouldn't have any problem. You should have low pressure and high temperature. So you need to explain. At low pressure, the gas particles are further apart in a larger volume. Okay, you need to mention this. Further apart in a larger volume. Hence, you may either say the intermolecular forces. Please take note, you need the intermolecular forces becomes insignificant. Okay, some of you may prefer to write about the volume. Please take note, if you write about the volume, you must ensure that you follow this format. Okay, you need to have the volume of the gas particles. Please insert a gas over here. Volume of the gas particles becomes insignificant compared to the volume occupied by the gas. Okay, please take note. Some of you who got this part wrong is just because by using your own words, you actually loses the essence of the statement. So please ensure that you have volume of gas particles insignificant compared to the volume occupied by the gas. Please take note. Okay, and hence gases tends towards ideality at low pressure. So at high temperature, I think quite a bit of you actually forgot to put in this point about higher kinetic energy. Okay, at high temperature, immediately of course link it to higher kinetic energy. And from then onwards, your intermolecular forces, again, please indicate between what? Between the gas particles become insignificant. Okay, and hence the gases tends towards ideality. You notice that in this mark scheme, we didn't award the marks for because the molecules have sufficient energy to overcome the forces of attraction. Please take note now, this part should be overcome the intermolecular forces of attraction. Please take note, it is because in this test we only want to focus on a few key points, but you need to write down this statement as to make your answer full, because in other questions we will award the marks for this statement. So this is still important. Please take note, you need to mention that at higher kinetic energy, molecules have sufficient energy to overcome the intermolecular forces of attraction. Okay, so this with this we have come to the end of the FA2 corrections.